Thank you, and good afternoon, everyone. I am Beatrice Branchini, and in this presentation, I'm going to give you an overview of what my PhD research focuses on and the goal for my 3 years of PhD, that is the creation of an hybrid hardware-accelerated quantum pipeline for next-generation genome analysis. But first, let me introduce myself. I am a third-year PhD student in information technology. But conversely, from most of my colleagues, my background is in biomedical engineering. And this is the reason why research for my PhD focuses on high-performance computing applied to the genomics domain. So let's start from the context. My project places itself in the personalized medicine domain, that we can say it is a medical procedure that has the goal to identify the best treatment to deliver to a patient depending on their specific diagnosis. Among the resources that are used in personalized medicine, there is the patient's genome that has to be computationally analyzed in order to identify those characteristics that make the patient unique under a medical perspective. There is an entire pipeline that allows you to go from a biological sample of DNA that can be taken from the patient's saliva or the patient's blood to get to help the clinician formulate diagnosis or to help pharmaceutical companies creating custom drugs. This pipeline takes a lot of time, but this is mainly due to the presence of a huge computational bottleneck that is represented by the genome assembly and the genome analysis stages. In particular, genome assembly focuses on the reconstruction of the patient's genome, and the genome analysis is the actual analytical process on this type of data. So to shorten this time span, we need to find ways to overcome this performance bottleneck. And to effectively overcome this bottleneck, we need to first understand which are the causes. So we have this bottleneck because these two steps have a large amount of data to analyze every run. But also, this is combined with the general purpose CPU's inefficiency when dealing with this type of data. And they are not able to keep up with the increasing amount of data that genomics applications are focusing on. So the idea in the state of the art is to offload compute-intensive stages, so compute-intensive tasks to hardware accelerators. Hardware accelerators, for example, GPUs or FPGAs, and there are both academic but also commercial solutions that already do that in the state of the art. Just think about NVIDIA Parabricks that focuses on genomics application accelerated on GPUs, or Dragon that accelerate genomic workloads on FPGA. The problem with all these solutions is that they get a lot of performance by accelerating the workload on GPU or FPGA, but this comes at the expense of flexibility. So there is still room for improvement, and we can go beyond the state of the art by combining two aspects. So this is the goal for my PhD thesis, is to combine domain-specialized systems focused on FPGAs and GPUs on which to offload the compute-intensive parts of the pipeline, but also new technologies, such as quantum computing, that can be used as a coprocessor in order to speed up the execution time. So this is the overview of the overall pipeline that I'm trying to create. It features a genome assembler that is going to be based on quantum annealers, and the pipeline will also feature quantum error correction accelerators to overcome the current problems of quantum devices. And these two stages are going to be followed by genome analysis hardware-accelerated algorithms. Just to give you an example of what I carried out during my PhD until now, firstly, I accelerated an algorithm that is called PER-HMM, that is widely used in the state-of-the-art to identify mutations within the DNA, and I integrated it into the state-of-the-art tool. And concerning the results, the approach that I used, that is based on hardware acceleration, but is while keeping an eye on the flexibility of the application, allows me to outperform all other hardware accelerated solutions in the state of the art but most importantly, enables me to preserve flexibility, so process genomic sequences regardless of the length they have. This is all on my side. Thank you for your attention, and if you have any questions, feel free to drop me an email or we can catch up later. Thank you.